Look around you for a second. The screen you're staring at, the chair you're sitting in, the stars up in the sky. They all share one incredibly basic trait. They have physical substance. But for decades, the absolute brightest minds on the planet hit a massive wall trying to figure out exactly how the fundamental building blocks of our universe actually get that physical substance. So, today we're demystifying one of the most mind-bending concepts in modern science, the Higgs boson.
It all really boils down to one simple but devastatingly complex question. Why does stuff have mass? We completely take it for granted, right? You pick something up, it has weight, it has mass, but when you zoom way, way down to the subatomic level, to the most elementary particles in existence, the math literally was not adding up. Explaining how these tiny building blocks acquire their mass was the central problem in particle physics for years. It just completely stumped everyone. Here's our roadmap for today. First, we'll look at the missing puzzle piece. Then, we'll break down the Higgs field versus the actual particle. After that, we'll track the 40-year hunt, dive into the massive discovery at the LHC, and finally, we're going to bust the myth behind the so-called God particle.
All right, part 1, the missing puzzle piece. To really grasp how huge this discovery was, we need to understand the theoretical wall physicists were up against. The Standard Model is basically our ultimate framework for understanding the universe's fundamental particles. But it had this one giant, glaring hole. According to the physics at the time, fundamental particles should theoretically be completely massless at really high energies. But at lower energies, we obviously know some particles do have mass. Figuring out exactly how they gain that rest mass, that was the missing puzzle piece holding everything else back.
Moving on to part 2, field versus particle explained.
Okay, so this is where the science gets a little heavy, but it is honestly brilliant. We've got to untangle two things that get mixed up all the time, the Higgs field and the Higgs boson. The Higgs field is a scalar field that exists literally everywhere, even in what we think of as completely empty space. It has a unique energy shape. Physicists often compare it to a sombrero, meaning it always has a non-zero value. Because it's basically switched on everywhere, it interacts with fundamental particles, acting almost like this cosmic molasses that slows them down and gives them their mass. That's the invisible grid doing the heavy lifting. Now, the Higgs boson, on the other hand, is not the field itself. It's produced by a quantum excitation of that field. Think of the field like a perfectly still pond. A splash creates a physical ripple. That ripple is the boson. And unlike that omnipresent field, this boson is incredibly unstable and decays into other particles almost the second it's generated.
So the tricky part was, if this invisible field is everywhere, how on earth do we prove it exists? Well, the math told scientists that this specific ripple, this massive scalar boson, had to have a highly specific fingerprint. They were looking for zero spin, even or positive parity, and absolutely no electric or color charge. Finding a particle with those exact properties was the only way to prove the whole theory.
Which brings us to part 3, the 40-year hunt.
Knowing what a particle should look like on paper is one thing, but actually catching a completely unstable ripple that decays almost instantly? That kicked off one of the longest scientific manhunts in history. It started back in 1964. Physicist Peter Higgs, along with 5 other brilliant scientists working across 3 different teams, proposed the Higgs mechanism. Fast forward through decades of fierce theoretical debates, the birth of a very sensational media nickname in 1993, all the way to 2012, when the monumental discovery finally happened. And just a year later, in 2013, the ultimate validation, the Nobel Prize.
Part 4, discovery at the LHC. 40 years. That is how long humanity waited to spot this fleeting, microscopic ripple. It took 4 decades of waiting for our technology to actually catch up to our math. It wasn't until 2012 that the ATLAS and CMS experiments at the Large Hadron Collider over in Switzerland finally pulled it off. The LHC is the world's most powerful particle accelerator. By smashing particles together at unimaginable speeds, they generated enough raw energy to excite the Higgs field. And bam, there it was, a subatomic particle that perfectly matched all those crazy specific properties we just talked about.
The impact of this was just astronomical. It was the final missing piece of the Standard Model. And because of this extraordinary real-world confirmation in 2012, Peter Higgs and Francois Englert were jointly awarded the Nobel Prize in Physics in 2013 for their theoretical predictions. Even though Peter Higgs is the name everyone knows, this was truly a massive collaborative triumph of human ingenuity spanning multiple generations. Finally, part 5, the God particle myth. Now, we really have to address the elephant in the room here. If you have ever heard of the Higgs boson, there's a huge chance you know it by its famous media nickname,
the God particle. This actually started back in 1993 with a popular science book by Nobel laureate Leon M. Lederman, which he literally titled The God Particle. It was catchy, it sounded super profound, and the media absolutely ran with it. They slapped it on every single headline, giving this microscopic scalar boson an almost mystical reputation.
But here's the funny thing. Actual physicists, they absolutely despise the nickname. Even Peter Higgs himself strongly criticized it. The scientific community sees it as a massive exaggeration that totally misrepresents the actual physics. It's not some mystical deity. It's a fundamental mechanical component of the quantum world. Honestly, an invisible field stretching across the cosmos that literally grants mass to the building blocks of reality, that's incredible enough on its own without needing a sensationalized title.
Which leaves us with this one pretty mind-blowing thought. We've proven the Higgs field exists. It's sitting right there with a non-zero value in every single inch of what we used to think was just empty space. It's secretly interacting with particles, giving them mass, and allowing stars, planets, and us to even exist. So, if a field this monumentally important was hiding in the math for 40 years before we built a machine big enough to prove it, what other invisible forces are quietly shaping our universe right now, just waiting for us to find them?